strategy.
Sure. Yeah. Folks, welcome to 6th lecture, and today we'll be talking about overvoltages in our power network. Normally, the network is supposed to work at the rated voltage. Rated voltage, as I have already explained it to you, rated voltages are the line-to-line RMS voltage. But the network comes across often some voltages which are superimposed on the rated voltage, and they are called overvoltages. Now, the overvoltages could be of two types. Let's first here explain what am I going to talk about. The types of overvoltages, the cause and source, standard shape of transient overvoltage. Transient, I hope you understand, which does not last continuously. Some phenomenon or something which comes and goes, that is known as transient. And how these overvoltages, mainly transient overvoltages, are produced. About the insulation level, that is the basic insulation level to the system, and transient overvoltage protection and insulation coordination, we'll talk a little later. So today I would like to apprise you about what is an overvoltage and what is the magnitude of overvoltages, because these are part of the network, and these also provide extra stress to the insulation. As I've been talking, insulation system is the base of power system, a base of electricity, and our object is to have the insulation system adequate. It shouldn't be less, it should be more. If it is less, it is dangerous. If it is more, it will cost more. It won't be economical. And the overvoltages also have to be taken into consideration when you design the insulation system of the network. So to say network means any gadget in the network. Let it be transmission line, generators, transformers, certificates, anywhere. So we'll be talking about the overvoltages which also are encountered by the network. Yeah. As I mentioned, some overvoltages are transient in nature, and the insulation system all over the power network must be designed to sustain overvoltage and not let cause any damage to the system. Now, we can divide the overvoltages of two types. The first one, steady state. I hope you understand steady state. For example, power frequency voltage in the network is a steady state voltage which lasts continuously. You can say source within the system, steady state overvoltage. The source is within the system. Power frequency overvoltage may last for a duration longer than 1 minute. So if it is lasting a few seconds or more than a minute, but the frequency of the overvoltage is the same as the rated as the, you can say, the rated power, rated system voltage. The frequency is the same as rated system voltage. That is steady state over voltage. This happens sometimes. We'll come to it. The second one is the transient overvoltage. Thus, as I mentioned, transient overvoltage are the ones which come and go, which do not last for a long time. Basically, the transient overvoltages may have a duration in microseconds or maximum in milliseconds. And these are impulse voltages. That means it's not power frequency voltage, it's an impulse voltage of duration in microseconds and milliseconds maximum. So there are two types of transient overvoltages. One develops within the system, and another one comes from outside. It is interesting. The lightning overvoltage comes from outside, although a lot of protection is given to the network. But it does happen that the lightning strikes on some of the conductor in the power system, is struck by lightning. And lightning, as you know, is an external source. And lightning injects heavy current, and that develops the voltage, and the system is running at its rated power frequency voltage. So the voltage developed by the lightning current injected on the conductor is superimposed on the rated voltage. Similarly, as you must be aware, there are a lot of switching operations which take place in the power system. Switching operation takes place at the circuit breakers. And every switching operation may result in switching surge. That means switching over voltage. And that switching over voltage could be of different magnitudes, like the lightning over voltage, which depends upon the magnitude of the current injected by lightning. Switching over voltage depends upon the just before the switching operation, the current in the network. It also depends on matters. It also depends upon factors like the instant of switching operation and accomplishment. That means at what exact instant of the current the switching is accomplished, is completely achieved. So we will learn what and how these voltages are produced. Yeah, let's talk about this is an interesting diagram. Estimation of magnitudes of overvoltages in per unit and their durations. As we can begin, there are four types of overvoltages. Three types of overvoltages and one, the rated voltage, highest voltage of equipment which is continuously there. So this is the magnitude of the voltage at which the system is operating. So in the system, there may be different levels of voltages. As you know, generation takes place at different, transmission at different, consumption is at different levels of voltages. So let's call it the system is operating at 1 per unit voltage. Okay. Then temporary overvoltage which may last in seconds. This is the second one, the temporary overvoltage, which may last in seconds. As you see, they may be more than the 1 per unit overvoltage, and actually the temporary overvoltage of power frequency take place due to certain reasons. Suppose there is a sudden load rejection. Some transmission line has to be taken away from the grid system. So the power supplied by that transmission line is interrupted, is no more there. So the rest of the system may develop higher rated voltage. This kind of things keep happening, and that gives rise to steady state or temporary overvoltages, which last in seconds and could also last in minutes. Then the third type of overvoltage, as you see it here, that is the switching overvoltage, which I just now mentioned, that takes place because of the switching operation at the circuit breakers. We learn how and how much and what are the factors affecting the magnitude of the switching overvoltage. And as I also mentioned, the switching as well as lightning overvoltages are transient overvoltage, and both of them last only for very short duration, and wherever they are developed, they travel throughout the system in the form of a impulse wave of higher voltage, and that when it travels in every direction wherever it is developed from, we call it traveling waves. Traveling waves are produced which spread in every direction where these impulse voltages are generated. You can imagine they would travel according to the impedance of the line, etc. We'll talk about it. Okay? And the magnitude, as you can see, of the switching overvoltage could be something more than 3 per units, as you see it here. It could be more than 3 per units. That means it is 3 times the voltage, rated voltage of the system. And again, it also depends upon the magnitude of the current which is interrupted, the instant at which the current is interrupted. When we say magnitude of the current, you can imagine under the fault conditions when the circuit breaker operates, the magnitude of the current would be very, very high. The fault currents are something like more than 100 times the rated currents. Then the second type of transient overvoltage is by the external source, that is lightning. That is when the lightning strikes on any part of the network, the location where it strikes upon develops overvoltage in either direction or in all directions, and that again is a transient overvoltage. Is again short duration. It moves in every direction in the form of traveling wave. So the difference between switching and lightning overvoltages, switching overvoltages may last having, we'll discuss the shape of the switching overvoltages, may have shape, or you can say the duration of rise and fall of the impulse wave in milliseconds, whereas lightning overvoltage lasts in microseconds. And lightning over voltage could be anything depending upon the magnitude of the current injected by the lightning strike. So that could be also that could be higher than switching over voltages. So as you can see here, it is going to the position of even 5 per unit system. And these are the real or actual voltage which may generate. And what happens, we to overcome these voltages, two methods are applied. One, as you can see, the green line here, as this is withstand voltage of equipment or the network, you can say. That is, the network is provided higher level of insulation in order to protect the system from overvoltage, not just the rated power frequency or rated voltage, also from the overvoltages. And there is some kind of a protection provided in the network with the help of, we call it lightning arresters, which divert the peak value of the overvoltage towards the ground. So this blue line, as you see it here, blue line, the voltages are limited in the network with the help of lightning arresters, because lightning arresters divert the peak value of the over voltage towards the ground. Only the residual voltage, what we call it, to be it remains in the network, and that is supposed to be much lower than the insulation level provided to the network. I hope you have got some idea about the overvoltage. Yeah. Steady state overvoltage, as I mentioned, happens when there is sudden load disconnection. Then there is just a minute. This could happen due to outage of a long, important high voltage transmission line. The transmission line may have to be taken away from the grid system because of so many reasons. Fault occurs, or some mainly because of fault in the system in that area. So you protect the rest of the power supply by disconnecting the faulted region with the help of transmission lines. So electrical faults, mechanical breakdowns, anything could be there for load disconnection. So steady state over voltages, one cause is load disconnection. And another cause of steady state over voltage is a sudden interruption of power supplied by one of the three phases. Suppose most of the system, as I said, are three-phase system. Suddenly, one phase has to be taken away. There is no power being supplied in one of the three phases. Two phases are continuing to supply the power. As in case of a fault condition, the fault happens in one of the three phases, that phase is immediately disconnected or opened. When no power is applied in that phase, that is single phase fault, you can say. In that condition, it could lead to severe situation of unbalanced load supply. We know most of the 11 kV and above, the system are considered to be a balanced system, that is, there is same magnitude of load in all the three phases. And this situation may arise that suddenly one of the phase is taken away. I'll draw this here one for you. If we take this here, and let's say this is the center point, this should be equilateral triangle, center point of the equilateral triangle, and this is your neutral. So voltages are equal when all the voltages are equal. Suppose this is taken away, this is taken away. Then what will happen that the neutral point will not be in the center of the triangle, it will be shifted. If the neutral point is shifted, let's say somewhere here, then you can imagine these two voltages, when you draw it with the shifted neutral point to N prime, you can say this is your N prime, and then the voltages in the two healthy phases, as you can see here, will be higher than the normal rated voltage. These dotted lines are longer than the full lines adjacent to it. So in these two phases, because of the shift of the neutral point, which is supposed to be on a balanced condition, center of the triangle shifts, and because of the outage of one phase in the other two phases, the voltage would enhance. So this is a unbalanced load distribution. This leads to unbalanced load distribution, and that is how the voltage in the two phases would be higher than the rated voltage. Now, the transient overvoltages in power systems are the impulse voltages generated at a single point in the high voltage network are spread in every direction from the point of generation in the form of traveling waves. That is what I tried to explain it to you. The high voltage circuit breakers operate within the system, and their operation gives rise to switching over voltage. Yeah, just a minute. Yeah, then the second source, as I mentioned, is the lightning over voltage, lightning surge also called. Over voltage, transient over voltage of impulse waveform is, or impulse wave, you can say, is also known as surge voltage, because it's a wave is also called surge voltage. The lightning over voltage, presence of metallic conductors, presence of streamer corona. Oh, that is being tried to explain why the electrical power network is prone to lightning strikes. See, the lightning prefers to strike upon a metallic conductor, because at the tip of the metallic conductor in the dielectric there will always be a high electric field. For example, suppose you take a this is a tip of the metallic conductor, and the clouds are here, and they have very high potential because of the charge accumulation there. They induce some potential at the tip of the conductor metal, but in the dielectric, this is the dielectric, air is the dielectric. Then what happens when the field density at the tip of the dielectric is high? There will be some kind of a partial breakdown phenomenon begin at the tip of the electrode. And this partial breakdown, what you have learned, we call it corona. Corona may happen there. The corona at such locations under sufficient electric field density, it develops in the form of streamer, we call it. This is streamer develops at the metal on the ground. This is all on the ground. So this is one of the reasons when the streamer developed on the ground at the metallic conductor. Streamer may develop here also at the clouds because of high potential, and these two streamers then develop into leader and propagate, one upwards and the one on the cloud downwards, they propagate and then they strike upon a thick leader by a thick leader, and in the process the charge or the current always acquires the least resistance path towards the ground. So the charge on the clouds is evacuated through this highly conducting leader. This is called leader channel, which is very highly conducting because the air acquires plasma state, so its conductivity is very high there. So the charge on the clouds acquires the least resistance path and evacuates. The current is flown on the conductor, and this conductor, because you can imagine the power system, our grid is all, practically all, overhead in the free atmospheric air, and that is how a lot of metal, because of the conductors in the power system, are spread for long lengths. So the power system becomes very highly prone to lightning strikes, because a lot of metallic conductors, the streamer corona, may keep going on also because of the rated voltage. So that, in fact, when corona activity is going on on the power system, some kind of corona activity, that is partial breakdown activity, keeps going on the power system network, and you would appreciate when the partial breakdown activity is going on, it ionizes the air, and the more or continuous partial breakdown or corona activity on the power system makes kind of a pre-ionized zone over the network. Wherever the high voltage transmission lines are going or high voltage open air substations are there, it because of the partial breakdown activity, a pre-ionized zone is formed, and the corona, for which corona is responsible for the pre-ionized zone. And when pre-ionized zone is built up, the air around there becomes a weaker dielectric than the air which doesn't have ionized particles, you can say, around. So the ionization, because of corona, develops a kind of a pre-ionized zone, weakening the dielectric properties of the air. So the lightning strikes, again, it, as I said, the weakest part of the system, the lightning prefers to strike on the power system. Yeah, when the lightning strikes on a conductor, this is a, you can say, a transmission line conductor, and the transmission line conductor is supported on the insulators. As you can see here, insulators you can represent with the help of capacitors, actually, because insulation forms capacitance, and on the other side is the ground. So when the lightning strikes because of the pre-ionized zone and metallic conductor, the current, let's say if there is a current, lightning current of I, then what happens, we can assume on either side of the point of lightning strike, the impedance to be equal on either side. So current gets divided into half. And here, as you can see, the current gets divided into half, on which flows on either side. Now, what happens? This line conductor would always have an impedance. It is connected to the network, and a metal would always have an impedance. And that impedance, there is a kind of a characteristic impedance of transmission lines, which I mentioned somewhere before and also in the previous lectures, which varies from 250 to 300 or 350 ohms, the characteristic impedance ZC. So the half the magnitude of injected current by the lightning multiplied by the characteristic impedance gives IZ, gives rise to an voltage. And because the characteristic of the current injected by lightning is in impulse shape, impulse waveform, the voltage generated is also of impulse form, and that 1/2 lightning current multiplied by the characteristic impedance, impulse voltage is produced from at the spot of lightning striking, or the location where the lightning strikes, and this over voltage doesn't stay there. It is superimposed on the network, the power frequency voltage of the conductor, and this impulse over voltage travels on either direction, as you can see in this diagram. And wherever insulators are there, first thing, it stresses the insulation, and whatever magnitude is feasible, it is possible, reaches to the substations, it reaches to other gadgets, transformers, circuit breakers, everywhere this over voltage reaches in the form of impulse over voltage, and in the form of traveling waves, you could say. The lightning, the typical wave shape, as you can see here, standard lightning impulse wave shape. This has been derived by a lot of measurement, actual measurements of the lightning impulse, and because it's a very, very fast wave, duration is in microseconds, so sometimes it is difficult to have its zero location. So people have taken something like 10% of the zero, above zero, and here it is also not sometimes possible to know the peak value because of the short duration in which the peak value is achieved. So 90% of the peak value. From 10% to 90% of the peak value is considered to be the rise time of the wave shape, and typical rise time of the wave shape is 1.2 microseconds. T1 is 1.2 microseconds. And impulse voltages are defined. The decay time, as you can see, the magnitude of the voltage decays. The time required to reach the 50% of the peak value is considered to be the time T2, 50% of the peak value, as you can see it here. And this 50% of the value T2 in this case is equal to standard lightning impulse wave microseconds. So the T2 is 50 microseconds, and the wave shape is defined as T1 by T2. So these are all in microsecond, very, very fast wave shape, and that over voltage, depending upon the very important, the magnitude of the over voltage developed will not only depend upon the characteristic impedance, which is constant for the transmission line conductor, but also upon the magnitude of the current injected by the lightning. And the lightning current may vary very fast. Lightning may vary from a few kiloamperes to up to, people have gone to up to 200 kiloampere. That is the peak magnitude of the impulse current injected could go up to 200 kiloampere. People have measured. So you might have observed sometimes the lightning has the leader, what you see in lightning, sometimes it is very bright, and sometimes it is not that bright, and the brightness depends upon the magnitude of the current. Higher is the current, the leader would be very, very bright, and more over voltage would be produced. Higher is the current, more over voltage would be produced. Now, let's try to understand what is switching over voltage. Or, as I said, these over voltages, lightning surge or switching surge also, we call it to be. The major reasons why the switching surge is produced is during the process of operation of the circuit breaker. That's making and breaking operation. But, by making, we say when the circuit breaker closes, and also breaking means when the circuit breaker opens the circuit. At circuit breakers in the circuit having large inductances and capacitance, because in the network there are three parameters in the network: resistance, inductance, and capacitance. So they play the role, and they together form the impedance. Now, large current flows in the inductance. In the inductance that is formed by the conductor, the magnitude of the current keeps flowing always. Also during the fault conditions, where as I said, the current could be 100 times. Now, what happens when we interrupt a fault? For example, when 100 times more current is flowing than the normal current, there is always some energy stored in the inductance. then what happens? What is that energy? You must have learned. Half I am taking small because of the instant value of the current, L, I square L, L. So this is the energy stored in any inductor. And this energy lies there for some time duration. And whenever we open, as you can see here, there is inductance in the circuit, there is capacitance in the circuit. At this instant, we are not bothered about the resistance because we have taken into consideration some current, some voltage has generated there. So, and this is a switch, as you can see, this is a switch. So, when the switch operates and interrupts a current, very high magnitude of the current, before that, the regular power supply voltage was there, as you can see it here. This is the voltage and current with time. So this is the voltage, power frequency voltage existed there always. Then this is the magnitude of the current, as you can see. At this instant, the current is open, the circuit is open. That means current stops flowing in the circuit. So when the two electrodes of the circuit breaker open at this instant of current, depending upon the magnitude of the current, there would be some energy stored in the inductance of the circuit. And that energy is released certainly. And that release of energy stored in the network gives rise to not power frequency voltage across, but it gives rise to overvoltage. And the overvoltage could be, as you can say, 2 U max. This is the U max, and the overvoltage could be 2 U max. So when we say here, if, as you can see, this is the instant when the current goes to 0. If this happens, this is an ideal condition for the circuit breaker to open. And when it opens at the current 0, because alternating current magnitude is fluctuating, when it opens at the current 0 situation, the magnitude of the overvoltage produced is twice that of the peak of the value of the rated power frequency voltage. So the overvoltage, you can say, if it is, this is the, we say U naught, that means the voltage with respect to ground of the system, and this is the peak value of the voltage. This is the peak value of the voltage, and that means if we take U naught here, U naught will be equal to U rated divided by root 3. That means the voltage with respect to the ground, and peak value of it, rated voltage is always given in RMS voltage. So the peak value what we are considering here, so you have to, the over voltage would be U naught multiplied by root 2 multiplied by 2. As you can see, the over voltage is twice of in magnitude of U max, and there we have considered the peak value of it. So U naught, which is in rated RMS value of voltage with respect, rated voltage with respect to ground, the peak value of it multiplied by root 2, and the twice the magnitude. So that is the magnitude of the over voltage, which is minimum actually, and it could be even more than that if the current is not opened under the condition of zero passing through, when it is passing through zero. Yeah. We can, okay, I'll explain in brief. If the current is not opened at current zero, at the instant value of the current when it is very, very high, you can imagine the energy released across the open points across the circuit breaker is the stored energy, and when it happens at some finite value of current, the energy released would be very, very high. So under that condition, the over voltage across the 2 points of the circuit breaker is also of very high magnitude. In that condition, the circuit breaker may try to let the current flow because of the high potential across the 2 electrodes in the circuit breaker. The dielectric strength is not enough between the 2 points to resist the current to flow when across. You can say when it opens, suddenly there is very high voltage across, and that high voltage reignites the current flow. That means there is again a short circuit within the circuit breaker. That means the current flow or the fault is reignited, and that may happen. We call it to be very fast switching transient when the dielectric strength of the modern circuit breakers between the 2 points is very, very strong. When the dielectric strength is not very strong. Sorry, when the dielectric strength is not very strong, the current may get reignited because the voltage across the circuit breakers reignites the current by producing a short circuit in the dielectric. So dielectric strength is, if it is not very strong, the current may reignite. So as you can read it here, the speed of switching operation or the electrode separation in the circuit breakers, these are the factors which determine, and the arc quenching characteristic or properties of the circuit breaker is not adequate, it is weak, arc is not able to be quenched, so it reignites. Restoration of dielectric strength of the circuit breaker electrode cap is very important. It should be restored, the dielectric strength of the cap should be restored in a better way so that reignition or the loss of insulating properties of the gap does not take place. The instant at which the arc across the electrode is actually extinguished, which represents the magnitude of the instant current, and hence the energy stored in the circuit breaker inductance, as I mentioned. Yeah, here is what I explained. As you can see, the arc gets interrupted, and the arc gets interrupted, but it reignites and gives rise to very high magnitude of the overvoltage. When a very high magnitude of the overvoltage is restrikes across the electrode gap, the insulating properties of the gap is lost, and the current again is able to flow between the gap. So this phenomenon may happen several times, and till finally the arc is interrupted. That may require some time, so that the dielectric strength of the gap is adequate enough not to reignite or not to lose its insulating property and not let the short circuit current reignite. So I hope I have made my point clear and you are able to understand what is happening within the circuit breaker. Yeah, we do provide overvoltage protection systems in the network that we will be talking about in the later lectures. And insulation coordination is also provided to the system, so that we have just adequate insulation. We provide just adequate insulation, no over insulation and no under insulation. We can learn in one figure. This is the basic insulation level, as I was mentioning. The basic insulation level, or BIL, for lightning impulse is defined as the electrical withstand voltage of insulation, expressed in terms of the crest value of the standard lightning impulse as per the specification in International Electrotechnical Commission. The BIL is chosen correctly relative to the prevailing protective level. Again, it depends upon the protective level. The equipment will have an adequate situation level to withstand the prevailing switching surges also. The BIL level takes care of lightning as well as switching surges. Switching surges are becoming more dangerous in the modern power systems because they are slower impulse wave compared to lightning. The slower is the impulse wave, or slower is the wave of the voltage, it may damage more the insulation. So you can say a dielectric would have highest Victorian strength for very fast impulse voltage. And which is the fastest impulse voltage? Nothing but the lightning impulse voltage. So accordingly, the insulation of different parts are designed. Now, surge diverters, I would like to explain on this diagram. This is a diagram which is explaining the role of the surge diverter. So the BIL, what I talked just now, is this is the BIL level, basic insulation level of the network. And then the protection level of the network. The lightning arrestor, this is a lightning arrestor, this is a lightning arrestor, as you can see, is always installed between a phase and between any phase and the ground. For example, for three-phase system, all the three phases would have separate lightning arrestors installed between the phase and the ground. When the traveling waves, this red one, as you can see here in this diagram, is the traveling wave, incoming traveling wave. When it reaches the circuit breaker, it grounds the peak, this part of the this peak part of the traveling wave, and what is let go beyond the circuit breaker is the residual voltage, as I was mentioning once. This is the residual voltage of the lightning arrestor, which is impressed across the lightning arrestor, and which is also the voltage which is let go inside the network. In the peak, the role of the lightning arrestor is to ground the peak value of the overvoltage. So now you can understand that when we design the insulation system, which is the base of the power system, we do take into consideration how much basic insulation should be provided so that the system is able to not only withstand the rated power frequency voltage continuously, but also on and off the impulse voltage or the over voltages faced by the system due to the lightning strikes, due to the switching operations, etc. Also, all this is designed taking into consideration the protective devices, level of the protective devices, working of the protective devices which protect the system from the peak value of the over voltage. And all these things have to be taken into consideration when we will be talking about the insulation systems, the performance of insulation. We will have to consider not only the power frequency voltage, but we will also have to consider the over voltages, lightning over voltage, switching over voltages also. So that is how we need in the laboratories also, not only a test voltage generator for power frequency voltage, power frequency high voltage, but also we have the impulse voltage generators, which these days we have impulse voltage, and also switching shape of the over voltage. You can imagine the switching over voltage. I did not, I think, give you the exact form of the switching over voltage. Switching over voltage varies unlike the lightning or like lightning. Lightning is very fast. Switching would, one of the standard wave shape is 250 by 2500. This is the rise time, and this is the fall 250% of the value. So you can imagine this is something like 0.25 milliseconds to, this is microsecond, this is in microseconds, and 0.25 milliseconds to 2.5 milliseconds. So this is a much slower wave as compared to 1.2 by 50 microseconds. So in fact, the importance of switching over voltages has increased as we have gone to higher and higher transmission line voltages, and switching over voltages could be more than 3 per unit and slower wave, so the insulation is stressed very highly, and we must design the system to be able to withstand the switching over voltages also. So thank you very much. We have learned about in this lecture how and to what extent the transient overvoltages are produced in the form of traveling waves, which spread all over the network, even up to the last point of the network is the most important one, is nothing but the consumer. It reaches the consumer from the point of generation till up to the consumer, through the transmission, through the distribution, it reaches to the consumer. Okay, thank you very much. See you tomorrow.